Okay, now we're going to do the basics of simple random sampling, just an introduction. I think you're all very aware of what simple random sampling is. It just means that you have randomly selected without any favor from your population, and we'll discuss in a few minutes the two different types of simple random sampling you can get, with replacement and without replacement. But what it means is, in the old-fashioned sense, you put, for example, people's names on or numbers on a little piece of paper, you crumpled it up, you put it in a hat, and you selected some. That would be an example of simple random sampling. And I've just told you about the different parameters of the population. You might be interested in estimating the population total, T, and you would do that by looking at I'll show you now. You can look at NY bar. So the sample estimate in the case of simple random sampling would be N times population size times the sample estimate. You would work that out because you have one sample and that estimates your total. If you want to estimate the population parameter and you've done simple random sampling, you would use the sample mean. If you want to estimate the population proportion that belong to a particular category, we'll be talking about that, you use the sample corresponding proportion. So, as I said, according to whatever you want to estimate, you would work out the estimator. These are the theta hat values, but also how well you estimate will be affected by the variance of the estimator. We've just spoken about that. So what we know is the sample type affects which estimator is best for any particular population parameter to be estimated. You can see here, obviously if you're estimating the total, it's a different formula than if you're estimating the population mean. If you want to estimate the T, you use an NY bar. If you want to estimate Y bar, you use little y bar. So it's different for the different estimators, in that depending whether it's that or that you're estimating the population total, you take the mean and you either just leave it or you multiply it by n. It depends on what you're trying to estimate, as you can see from that diagram. So it's also what you're estimating that will determine what you're working out from your sample. But another thing that estimated is your choice of sampling type. If it's not simple random sampling straight from the whole population, if it's, for example, systematic sampling, there's a whole different formulas, and even different, even these things, the sample statistic will change totally if you're doing stratified sampling or if you're doing systematic sampling. This will change these estimators, but another thing that will change is the variance of that estimator, which you need, because you're going to say, this is the estimator, and then you make a confidence interval around it, which is the variance. All of that changes for different sampling types. So, simple random sampling with replacement, we're going to call SRSWR. What does that mean? It's as if you've got a bowl and you select one out, and then with replacement, you replace again before you select the second time. We've got small n number of elements we want to select from your capital N, the usual way. So we want to select little n from big N, with other words, the sample from the population. So these are all different values. It's different people, n of them. What it means if it's simple random sampling with replacement, the sample of n could have the same person twice. For example, in this class, suppose however many there are of you today, that's capital N, and I want to select 3 people, but it's with replacement, then I could pick this lady 3 times. Just, it turns out, I'll pick the same person twice. That's with replacement, obviously. Without replacement, it's just called SRS. Now, with other words, if you see use SRS, simple random sampling, you always assume it's without replacement. Because the normal way, if you say pick 3 people, why would you pick the same one twice? Pick 3 people doesn't mean you can pick the same one twice. Okay? So that's why that doesn't have a WTR or something like that. Simple random sampling, if nobody says with or without replacement, always assume it's without replacement, because that's the obvious thing. If somebody says, yes, 500 people's name, pick 3, you would pick one, and you wouldn't pick him back before you pick the second one, right? It's unusual to put them back. That's why you need a special code if you are doing with replacement. So we're going to look at simple random sampling. In the first case, we're only going to estimate the population mean. So the theta is the population mean. That is what I want to estimate. What is the estimator? You know it's a sample mean. And I'm going to say, okay, I also want a formula for the variance of the sample mean, because different samples would give me different estimates. You know this is a constant. And we want to know how best we can estimate it. So in this particular case, you know now this is just notation so that you can follow a book if you want to look at it. Your population has got capital N values. You've got readings on each of the population elements in the sample. Y1 to Yn, for example, N people and their heights would be that. That's my population. There's something I want to estimate about them. I'm going to use my sample. So I select these people. So how we think of it, the population. If I want to estimate, the thing I want to estimate is the population mean. I want to estimate, obviously, what is the mean. Add the values up in the whole population up to big N and divide by how many there are. And I estimate the population mean. Remember, I've just done it in the previous slide, obviously, with the sample. So from your sample, you don't know the population, you just pick from them, you end up with a sample, say it's height, you know there's 17,000 people, you select 150 and you measure each one and you got their height, so you've only got readings. These Y values, Y1 to Y little n, you have those values, you don't have those values, you haven't measured all 23,000 whatever, so you select and then you do something on the sample because you're trying to estimate, use the sample mean to estimate the population mean. So you're hoping that this will estimate that, knowing full well that this is a constant, but this is a variable. Because it's a variable, it's got a variance. I want that variance to be small. Now there's something you need to know the expression of. It's called S squared, and that's, if you look at this, it's a formula you need to know. S squared is sum from i's 1 to n, yi minus y bar squared over n minus 1. If you look at that, what is that? It tells you yi minus, let's start from the middle here, yi minus y bar squared. It says how far is yi minus y bar, forget the square for this case. It's saying add together how far those values are from the middle. You're squaring just because some are positive and some are negative differences, and they would cancel. Say the one is plus 3, that difference, the other one is minus 3, they would cancel each other out. That's why you square. You're just saying there's a value in the middle that's y bar and there are values all over the place. The mean is here and the y's are all over. How far on average, squared average, are they? The fact that you're dividing by n minus 1 is just to ensure that it's an unbiased because you've calculated that y bar, but don't worry about that. Basically, it's sort of, think of it as an average square distance from the mean. This will definitely tell me how much do my y's actually vary around this y bar. Can you see that? There's similar formula for the sample, just like this is sum through the population, how far the population values, all of them, differ from their mean. You do exactly the same for the sample, and that's called little s squared. That's a measure how much your elements in your sample vary. You generally don't know big S squared, but you certainly would know little s squared, because little s squared, you've got all the sample values. You see, the beauty of your sample is you've got little y1 up to little yn. So you can definitely calculate that, and you can definitely calculate that. You can calculate what we call sample statistics. You can calculate the sample mean, you can calculate the sample S squared. You can never calculate these two, but you're trying to estimate them. So we have these two sample statistics, but we don't know the population parameters. And the main thing we want to do is estimate this population mean with the sample mean. We want to estimate this using that. But I'm actually going to, in the end, use that as well, because that's what I use to calculate my variance of my y bar. So now I'm going to give you simple random sampling with and without replacement, I'm just giving it to you. I could prove it, but I'm not going to. I'm going to give you a table where I will state, if I'm using simple random sampling with replacement and without replacement, how do I, you see that Y bar's got a hat. It says, how do I estimate the mean of the population if I use simple random sampling without replacement or simple random sampling with replacement? That's how you do it. Simple random sampling without replacement. You want to estimate the population mean, you use the sample mean. We've already done that in that little theta parameter thing I showed you. If it's with replacement, you also use the sample mean. Simple random sampling with or without replacement. If you want to estimate the population mean, you use the Y bar. So I've got my population, I select a sample. I work out the mean of the sample. I just say that's an estimate of the population mean. But that's not enough, because your sample mean could be far away from the true value or could be near, you don't know. So what you do is you give a confidence interval. You've got to say, this is the sample estimate, I hope it's close to the true value, but I'm 95% sure it's somewhere between this and this. So that is the next thing you do. You've got to be able to give your variance. What is the variance of the population parameter estimate, with other words, of this little Y bar? And it's this thing. The real variance is given by 1 over n, 1 minus n over n, big S squared. That's a big S squared. That's the S squared I've just shown you in the previous one, the population S squared. But if it's the simple random sampling with replacement, it's different. It's got a 1 over n, 1 over n, 1 minus n over n. Can you see where the difference is? Who can see the difference? What's different? That's different. With replacement, it's got an n, little n. Sorry, with replacement, it's got a 1 there. Without replacement, it's got an n there. Other than that, it's identical. This is really the only formula you should have to remember. 1 over n, 1 minus n over n is squared. You must know that. It's something you must think in your head all the time. And I'll tell you why it's important. Once you know that, all you have to know, simple random sampling with or without, you use sample mean to estimate. That's my estimate. The variance of the estimate, if you know that formula, then you must know, okay, the n becomes a 1 if it's with replacement. It's not hard to remember. If you know that, you can easily remember that one. Take out the n and make it a 1. But now, if you wanted to calculate the estimate, you would say, what is the confidence interval? It's the estimate, with other words, Y bar, plus or minus twice the square root of the variance. So you go twice the square root of this. But this is a S squared that's got all the population values in. Because if you go back to the previous page, look what S squared is. It's the population, but you don't have the population values. That's not going to help you. So to get your confidence interval, you want to calculate this, because you want to say that plus or minus twice the square root of this, but this has got all the population values in. That's why I said you have to estimate the variance. And that's why this comes in now. It's exactly the same formula, but the big S became a little s. So that's what you do. You say my population parameter, Y bar, is equal to this sample mean plus or minus twice the square root of this, and you know n value, you've got a sample. This is just all sample values to calculate that. Can you see? N you know because you've got a frame with all your, you'll know how many students you're picking from, or how many, whatever your population is. So all of this is known. And you work out your Y bar. So you just say Y bar plus or minus twice square root of this. But then that's without replacement. This is all, this first column is, this is all for without replacement. What is it if it's with replacement? S squared over n. It turns out to be S squared over n. So you can see it's slightly different, right? So now the question is, what is the difference between sampling with replacement and without replacement? Remember I said if we just say simple random sampling, assume it's without replacement. With replacement, now before I go further, suppose I'm going to estimate the population mean. What do you think, which one should be more, give you better results? If you're replacing, suppose I want to work out the average weight and there's someone big in the class and I pick him twice. You think that's going to give me some bias? If you're replacing, I'm going to pick 4 people and I happen to pick somebody really tiny or somebody really big and I pick them twice. It's going to make my sample mean look bigger or smaller than it should, right? So I'm sure you can imagine with replacement should give you worse results than without replacement. But in both cases, I'm going to use sample mean, whether it's with or without replacement. If I want the average mass or weight of a person in the class, I pick a sample. If it's with replacement, and you pick that, you're taking the mean whether it's with or without replacement. With replacement, you should get worse results. What does that mean? Wider confidence interval. What does that mean? Oh, it must mean the variance is a bigger number. Because the thing that stretches your confidence interval is that variance. Okay? That's just an obvious thing. Both whether you're using with and without replacement, whether it's simple random sampling or simple random sampling, it should have been with replacement written here, results in your estimate being the estimate of the mean of the population. Use the sample mean, we know that. But the formula is different. And the reason for that, if you look back at the previous page where I said this is how you estimate the variance, this one had just the S squared over N. Whereas this one had all this in front. Now if you look at this, that is S squared over N and that's S squared over N. This is identical to the previous page. Think about this, 1 minus N over N. This is the whole population. This is how many, so this is the fraction you got from the population. If I pick half the population, suppose there's 100 in the set and I pick 50. 50 over 100 is a half. 1 minus a half is a half. So you take the S squared N and you multiply by a half compared to this S squared N. And you see. So this 1 minus F over N has to be a fraction. So you take the same variance you would have got, the estimated variance, in with replacement. If you're doing without replacement, you take the same variance and you go and multiply by a fraction. Because it can't be bigger than 1. It's 1 minus, and this is a fraction. So this is always going to be smaller. What does that mean? That means that this is going to give you better results. Smaller variance is always the good thing. So you can see that this is actually always going to make your variance smaller. We call it the continuity corrector. And we'll talk about that. What they really mean is these two are identical, S squared over N, S squared. And they put this in, they say continuity corrector. You can't continuously just keep sampling, because if you're sampling and you replace, and you're sampling and you replace, you can continuously sample. It never stops because you keep replacing. And they say it's continuous sampling. So that's a continuity corrector. With other words, this would be S squared over N, and with replacement would be, if you could replace and sample until it's continuous, you never stop. That would be S squared over N. So if you're without replacement, you have the same variance as is in the case of continuous sampling, because with replacement is continuous sampling. But because you multiply it by this thing, that's called the continuity corrector. So what we have then, with other words, in the case of simple random sampling, it's you take the variance of S squared over N, which is the variance of with replacement, and you multiply it by this fraction, 1 minus N over N. That is a fraction. So what it means is without replacement, always with a smaller variance than simple random sampling. With replacement, when you're using the sample mean, obviously, because the biggest little n would be equal to 1. Oh, sorry, the biggest little n could be is if you sample the whole population, your sample size will be big N. Then this would be 1 minus big N over N, and that would actually be a 0. And we'll talk about that just now. What does that mean? That means that it's a constant. Your population mean is equal to your sample mean because you sampled everybody. So it doesn't vary, so that makes sense, by the way. So what it means is simple random sampling without replacement, it's got a smaller variance than simple random sampling with replacement. But that's obvious. Without replacement is when you can't sample the same person twice. Smaller variance, better result. You would expect to get better result. So that's obvious. It's more efficient. It's much better. So when you want to estimate the population mean using simple random sampling, is always going to give you better results if you do without replacement than if you're doing with replacements for the same sample size. So now if we use simple random sampling with replacement, for example, to estimate the population mean, what could you do to make the estimation actually without replacement? I must change that. I can't do it once I'm presenting, but simple random sampling without replacement, apologies, this should have read without replacement. If you want to estimate the population mean, what would make your estimation better? Let's look at the formula without replacement. This is the formula, 1 over n, 1 minus n over n, little a squared. Now, what would make it better? Look at the n, and I've highlighted it. If your sample size n is bigger, what's it going to do? Look here. You divide by n and you're subtracting n. The bigger n will make your variance smaller. If you're dividing 1 over 100 or 1 over 2,000, this is always going to be smaller as n gets bigger, because bigger here will make this smaller, and also bigger here you're subtracting. The other things are fixed. Your big N is fixed. So the bigger the sample size, the smaller the variance. Isn't that obvious? Think about it. You're sampling. If I'm sampling 2 of you to work out the mean, while sampling 10 of you, you're going to get more accurate as you sample more. More accurate means the variance of the estimator gets smaller. So the larger the N, the bigger influence on your variance. You can see big N will actually make your variance small. It means your mean won't differ so much. If I work out the mean of 10 of you, your average height, and I pick a 10, or I pick another 10 and another 10, the means won't differ so much if I pick 10 as if I pick 2, 2, 2, and look at how much the means differ. See, I want you to have, that's what I need you to have for the test and the exam, to understand the concept. You should be able to see that as the n gets bigger, this formula gets smaller. The answer would get smaller. If the s squared stays the same, your n's bigger will make this smaller. This smaller means better results. You always want a small variance. The larger the sample size, it will decrease the variance, obviously. So when you're conducting simple random sampling, you must note the role of the sample size. Always bigger sample size, chosen without cheating, giving everybody an equal chance, because a simple random sampling will make your variance smaller. Variance smaller means confidence interval shorter, because it's y bar plus or minus twice square root variance y bar. And this is variance y bar. So you can make it small. If your S squared is big, it's fine. As long as if your S squared, which is actually an estimate of the population, is S squared. If you find that your confidence interval is too wide, then all you have to do is sample again, sample more, make it a bigger N, because that can bring it down as well. And that's the end of today.